Do you know that for any angle alpha, there is another angle alpha prime as close as you want to alpha, such that the values of sine and cosine and tangent are all rational numbers? Moreover, the numerator and denominator of these rational numbers form a Pythagorean triple. So 120 squared plus 209 squared equals 241 squared. And in fact, all such angles come from a Pythagorean triple. So how did I find this triple in particular that is close to the angle 30 degrees? It is well known that the values of sine of alpha and cosine of alpha can be parameterized, simply because we can parameterize the circle in terms of our parameter t. If I want to approximate sine of pi over 6, which is a half, I can use the parametric form of sine of alpha and solve for t. This is equivalent to this quadratic equation, which I can solve using the quadratic formula. So t is 2 plus or minus the square root of 3. Now what I want are rational numbers t that are as close as I want them to be to 2 plus the square root of 3, for example. If I want to find rational approximations of 2 plus the square root of 3, I can use what's called the continued fraction, which is going to give me the best rational approximations of that irrational number. The continued fraction in this case is 3 plus 1 over 1 plus 1 over 2 plus 1 over etc. And then it's 1, 2, 1, 2 repeating. And now to find rational approximations, you can stop the continued fraction at different points. So for example, here that tells me that the number is approximately 3. If I stop here, that tells me the number is approximately 4. If I stop here, then that gives me a different rational approximation. Those rational approximations are called convergence of 2 plus the square root of 3 and are the best rational approximations of that number. And those are 3, 4, 11 thirds, 15 over 4, 41 over 11, etc. And now I'm going to plug in the rational approximations of 2 plus the square root of 3 into these formulas to get values of sine of alpha and cosine of alpha and to get a Pythagorean triple that approximates these values. And for t equals 3, I get the 3, 4, 5 Pythagorean triple. For t equals 4, I get the 8, 15, 17, and so on. And for 15 over 4, I get 120, 209, 241, which is the one I used for the approximation, but this one is better. And notice that 120 divided by 241 is really close to a half, and 209 divided by 241 is really close to the square root of 3 divided by 2. Let's do this again, but for pi over 4. The tangent of pi over 4 equals 1, and the parameterization of tangent is 2t divided by t squared minus 1. So let's find rational values of t that approximate 1. Like before, that leads me to this quadratic equation, and it tells me that t has to be 1 plus or minus the square root of 2. So now I need rational approximations of, say, 1 plus the square root of 2. The continued fraction of 1 plus the square root of 2 is actually really easy. It's 2 plus 1 over 2 plus 1 over 2, etc. It's all 2's. Therefore, the best rational approximations of 1 plus the square root of 2 are 2, 5 halves, 12 over 5, 29 over 12, 70 divided by 29, etc. And those values of t, for example, 2, leads again to the 3, 4, 5 triangle, but as you go down, for example, 29 over 12 leads to the Pythagorean triple 696, 697, 985. Notice that all these Pythagorean triples are such that these two numbers differ by 1. And that's because they have to approximate pi over 4, which is 45 degrees. So they are Pythagorean triples that are trying to approximate a 1, 1 square root of 2 triangle. So 696 divided by 985 is a very close approximation of a square root of 2 over 2. And so is 697 divided by 985.